welcome to the deep dive. Tonight we are looking at a piece of engineering that, honestly, it feels a little bit like magic the first time you see it in action.
Oh, absolutely. It's one of those things where the math just works out so perfectly.
Yeah, exactly. So if you've ever used a modern AI coding assistant or a massive language model, and you've watched the text just stream onto your screen at warp speed,
Right.
you've probably wondered, how is it physically doing that?
Right, because the hardware constraints are so rigid.
Exactly. So we have the answer for you tonight. Whether you're a web developer up late refactoring legacy code, or maybe a back-end engineer prepping for a system design interview, or you're just staring at your terminal wondering what's actually happening under the hood, this one is for you.
It's a great topic. We're unpacking a brilliant algorithmic trick from our source notes called speculative decoding.
Speculative decoding. And it really is a fascinating piece of system design.
It really is. And to understand how it works, it actually helps to start with a very human analogy from the source material.
Okay, lay it on me.
Imagine you are at a restaurant with a friend, and this friend is incredibly predictable.
We all have one of those.
Right. They always, without fail, order the exact same thing. So before the waiter even makes it to the table, you just speak up and say, he'll have the grilled salmon, no lemon, extra asparagus, and a sparkling water.
And your friend just nods.
Exactly. Your friend nods. You guessed perfectly. The waiter writes it down in 5 seconds flat, and you've completely bypassed that usual, back and forth menu ritual.
Right, so you're taking a shortcut based on a highly probable prediction. But what happens if the prediction isn't perfect? Like, say you guessed all of that, but your friend actually wanted a still water today, not sparkling.
Well, your friend just jumps in and corrects that one single item, and the waiter notes it down. Even with that one correction, that entire process was still significantly faster than if you had just sat there and let your friend order from scratch one single item at a time.
Right, because they didn't have to say the salmon and the asparagus part all over again.
Exactly. That is the core dynamic. If we translate that to the software world, think of it like a fast, eager junior assistant and a meticulous senior editor.
Oh, I like that.
Yeah, the junior assistant can draft a whole paragraph in no time at all. It might not be perfect, but it's exceptionally fast. Then, the senior editor reviews that paragraph in a single glance.
Just scanning it.
Right. The editor accepts most of the words and just tweaks the few that are slightly off. Now, the senior editor absolutely could have written that entire paragraph herself, word by word, from a blank page.
Sure.
But checking someone else's draft is fundamentally faster than creating it from scratch.
Which establishes the foundational thesis of this entire deep dive. Verification is cheaper than generation.
That's it. That asymmetry is the beating heart of speculative decoding.
Verification is cheaper than generation.
Yeah.
But to really appreciate why we need this solution, we have to unpack the problem. And for you, as a software engineer who might not spend every single day building machine learning models, the hardware constraints here get incredibly real.
Very real. We have to talk about the latency problem.
Yes, the bottleneck. Break it down for us.
The fundamental pain point of autoregressive generation is that it is strictly sequential.
Meaning one after the other.
Exactly. When a large language model generates text, it produces token 1. Then it has to use token 1 to generate token 2. Then it uses tokens 1 and 2 to generate token 3.
So you can't cheat and skip ahead.
No, you cannot start step n plus 1 until step n is completely finished. It is an unbreakable sequential dependency.
Let's put some numbers to that so you can really visualize it. Say you are running a 70 billion parameter transformer model. On state-of-the-art hardware, a single forward pass generating one single token takes about 30 milliseconds.
Which doesn't sound too bad in isolation.
Right, 30 milliseconds is tiny. But if you want to generate 100 tokens, which is really just a short paragraph, that's 3 seconds. For 1,000 tokens, you're waiting 30 seconds.
The latency scales linearly.
Exactly. And if you're building an interactive coding tool right in an IDE, and the user has to wait 15 seconds for a function autocomplete, they're just going to type it themselves.
Oh, it ruins the user experience entirely.
Yeah, they'll just uninstall the plugin. So if you're a systems engineer looking at this bottleneck, your first instinct is usually just to throw more compute at the problem, buy faster GPUs.
Right, but here is the GPU paradox. For single token generation, your extremely expensive GPU is actually sitting there vastly underutilized.
Wait, it's underutilized, even when it's taking 30 seconds to write a page of text.
Yes, we've spent billions building hardware for parallel processing, but we're using it to play a sequential game of dominoes.
For those of us who don't live in PyTorch every day, what does that actually mean at the hardware level? Why is the GPU bored if it's taking so long to generate the token?
It comes down to how data moves inside the chip. Generating a single new token involves multiplying the new token's query vector against cached keys and values from the previous context.
The KV can
Exactly. That specific operation is a matrix vector multiplication. GPUs are engineered for massively parallel matrix multiplications, where thousands of arithmetic operations happen simultaneously.
So it's the wrong type of math for the hardware.
Right. With a matrix vector operation, you're only using a tiny fraction of the GPU's compute cores. The real bottleneck is moving massive amounts of data from the GPU's main memory, the HBM, into the fast RAM where the math actually happens.
So it's essentially a traffic jam.
Precisely. You are not waiting for the arithmetic to finish, you are waiting for the data to load. In engineering terms, you are memory bandwidth bound, not compute bound.
Okay, so we have this painful hardware reality. The GPU is the bottleneck because we have to wait for each sequential step to finish. But at the same time, the GPU has all these idle cores because each of those steps doesn't have enough parallel math to keep it busy.
It's a frustrating paradox.
No amount of throwing raw hardware at a sequential constraint is going to fix it. We need an algorithmic trick.
And that brings us back to the breakthrough insight. Verification is cheaper than generation.
The editor and the assistant.
Exactly. We know that conceptually from our editor analogy. But how does that actually manifest inside a neural network? Suppose I hand a massive language model 5 candidate tokens all at once and ask, would you have generated these 5 tokens?
Okay.
The model can answer that question in a single forward pass.
Wait, a single forward pass for 5 tokens. How is that possible if the model is normally forced to be sequential?
Because of how transformer models handle the prefill phase, when you first send a prompt to an AI, say a paragraph of instructions, it doesn't read it one word at a time. It processes the entire sequence simultaneously.
Oh, right. The prompt is processed all at once.
Yes, it computes the probability distribution for the next token at every single position in parallel. So if you give the target model your original prompt plus 5 draft tokens, it evaluates all of them at once.
In parallel.
In parallel. It will tell you the probability it assigns to each of those 5 draft tokens given their prefixes, all in one go. And because the GPU has all that underutilized parallel capacity we just talked about, running that single forward pass for 5 tokens costs roughly the same amount of time as generating a single token.
That is wild. That is the asymmetry in action. Generation of 5 tokens equals 5 slow, sequential forward passes, fetching data back and forth from memory every single time. Verification of 5 tokens equals 1 fast parallel forward pass, doing all the math at once.
Exactly. So the algorithm basically works in 3 steps. First, the draft.
The eager junior assistant.
Right. You take a small, fast model, maybe 1 or 2 billion parameters. It runs 10 to 20 times faster per token than your massive 70 billion parameter target model.
Because it fits easily in memory.
Yep. This draft model rapidly spits out a sequence of guesses, let's say 5 tokens. Next is the verify step. You take your massive target model, you hand it the original context plus all 5 of those draft tokens, and it runs that one single, highly parallel forward pass.
The senior editor reads the paragraph.
Yes. For each position, it computes the probability it would have assigned to that specific draft token.
And then the third step is accept or reject. You start from the first draft token and compare the draft model's prediction with the target model's prediction.
Right.
If it matches the target model's expectations, you accept it. If it doesn't, you reject it. Resample a new word from the target model and immediately discard any remaining draft tokens after that rejection point.
That's the flow. Draft, verify, accept, or reject.
But let me play the skeptic here for a second. If the draft model's only 1.5 billion parameters, isn't it just going to hallucinate complete garbage half the time?
That's a very fair concern.
Right, like if you're building a production system, you hear draft model and immediately think you are trading quality for speed.
Yeah.
How does the big model fix a draft that is fundamentally wrong?
That is the most common hesitation engineers have when they first hear about this. But here is the magic, and it's a key takeaway from our sources. This is a mathematically exact method. There is 0 quality loss.
0. None at all.
None. It relies on a classic statistical technique called rejection sampling. The architecture guarantees that the final output distribution exactly matches what you would have gotten if you had only used the massive target model.
Okay, let's break down that guarantee, but let's keep it audio-friendly for the listeners. We don't need to read out raw algebraic formulas here. How does the math actually ensure we aren't degrading the output quality?
It's actually quite elegant. It just looks at the two probabilities for a given word. If the big, massive model is more confident in the draft word than the small model was, it's an automatic yes. You accept the token.
But what if the massive model is less confident? Say the tiny model was 80% sure the next word should be apple, but the massive model looks at it and says, I'm only 40% sure it should be apple.
In that case, you don't instantly throw the word away. Instead, you basically roll a weighted pair of dice based on the difference between the two probabilities.
A literal dice roll inside the algorithm.
Exactly. If the dice roll succeeds, you keep it. If it fails, you reject the token. But if it gets rejected, you don't just lazily take the massive model's top choice.
Because that would skew the math.
Right. You sample from a specifically adjusted distribution that corrects the bias of the draft model. Every single token in the final output, whether it was accepted from the draft or resampled after rejection, comes strictly from the target model's true statistical distribution.
Look at it this way. Let's make this totally concrete with a real example from the source data to see the speed up in action. Let's set the scene for you.
Okay, let's hear it.
You have a massive 70 billion parameter target model, and you've got a much smaller 1.5 billion parameter draft model. The prompt is, explain photosynthesis in one sentence.
Classic prompt.
Right. So far, the model has output. Photosynthesis is the process by which, and now we need the next 5 tokens.
We enter the drafting phase. The small draft model fires up and auto-regressively generates 5 tokens. Plants convert sunlight into chemical.
Plants convert sunlight into chemical.
Exactly. Because it's a tiny model, each token takes just 2 milliseconds. Total drafting time, 10 milliseconds.
Now we verify. The 70B target model takes all 5 of those draft tokens at once. It runs one massive parallel forward pass, which takes 35 milliseconds, and it scores them.
Right. So let's look at the scores.
Position 1 is plants. The target model gives it a probability of 72%. The draft gave it 65%. The target is higher, so it's auto-accepted.
Position 2 is convert. Target gives 58%, draft gave 45%. Again, the target probability is higher, auto-accepted.
Now, position 3 is interesting. The token is sunlight. The target model gives it a 40% probability, but the draft model was overly confident and gave it a 52% probability.
So because the target is lower, we don't auto-accept. We have to roll the weighted dice. Let's say we have roughly a 77% chance to keep it.
We roll the dice, and for the sake of the example, it passes, it's accepted. Then for positions 4 and 5 and 2 in chemical, the math works out in our favor again, and both are accepted.
Look at the final result. You got 5 tokens accepted. The draft took 10 milliseconds. The verification took 35 milliseconds. That's 45 milliseconds total.
45 milliseconds. And if we didn't use this trick,
If you had just run the 70B model autoregressively, 5 sequential passes at 35 milliseconds each would have taken 175 milliseconds. You just achieved a nearly 4x speedup with mathematically identical output quality.
let me push on the failure mode, though. What if that dice roll on token 3 failed? What if sunlight was rejected?
If token 3 is rejected, you keep tokens 1 and 2, plants, and convert. You resample token 3 from that adjusted distribution we talked about to fix the bias, and tokens 4 and 5 are completely discarded. They never happen.
You just throw them in the trash.
Yep. But even in this scenario, think about the time. You still generated 3 valid tokens in 45 milliseconds. Sequentially, 3 tokens would have taken 105 milliseconds. So even with a rejection right in the middle wiping out half your draft, you still get more than a 2x speedup.
That is incredible. So we have this perfect mathematical trick, but perfection on paper usually meets a harsh reality in production. Managing 2 separate models sounds like an absolute DevOps nightmare.
Oh, it really can be.
You have to load 2 models into memory, they have to share the exact same vocabulary, they have to use the exact same tokenizer. If your deployment gets out of sync, your text generation completely breaks down.
Yeah.
How are engineers actually deploying this without losing their minds?
The community recognized that operational friction immediately, which led to some fascinating alternative architectures that completely ditch the 2-model setup.
Okay, so just one model.
Right. One of the most prominent is called Medusa.
Medusa, like the mythological monster with the snake heads.
Exactly like that. Instead of running a separate draft model, Medusa modifies the target model itself. Normally, a language model has a single output head predicting the next token. Medusa adds 3 to 5 small, lightweight prediction heads right on top of the base model.
So while the main head is doing the heavy lifting to predict token 1, these extra Medusa heads are predicting token 2, token 3, token 4, all simultaneously.
Exactly. You construct candidate sequences from these heads and then verify them in parallel. It completely removes the need for a second model in memory.
because they're just bolted onto the main one.
Right. And because these heads are trained specifically on top of the base model's internal representations, they are highly accurate at predicting what the base model wants to say. You generally see 1.5 to 2.5x speedups with Medusa without the DevOps headache.
That makes a lot of sense. But our notes also highlight another approach called EGLE. And EGLE takes a very different angle.
Yes, EGLE is fascinating.
Instead of adding output heads, EGLA trains a super lightweight model directly on the hidden states of the target model's second-to-last layer. Now, for a back-end developer listening to this, what does that actually mean? What is a hidden state, and why is it useful for drafting?
It's a great question. Think of the hidden states as the concept layer or the vibe layer of the neural network.
The vibe layer.
Yeah, deep inside the network, right before the final output layer turns everything back into human-readable text, the model represents its thoughts as dense mathematical vectors. These hidden representations are incredibly predictive of what the model is about to say next.
So it already kind of knows what it wants to talk about.
Exactly. By drafting in that rich feature space, the realm of concepts, rather than the raw token space of actual words, EGLE can draft highly accurate sequences very quickly. It's like predicting the trajectory of a thought before the words are even formed.
Predicting the trajectory of a thought. I love that.
This method yields massive 2 to 3x speedups.
That is wild. Drafting in the concept space. Now, if you want zero extra training and zero extra models, there is look-ahead decoding.
Yes, look-ahead
It
decoding.
uses a mathematical approach called Jacobi iteration. In plain English, instead of guessing tokens left to right like a normal draft model, it throws down a bunch of random placeholder tokens all at once and then rapidly refines them in parallel until they form a coherent sentence.
Which sounds completely backwards, but it works.
It's a more modest speedup, about 1.5 to 2x, but the beauty is you can drop it onto basically any existing transformer model without changing the architecture at all.
And there are other specialized flavors, too. If you're serving a model that generates a lot of highly predictable boilerplate, like an AI generating React components, you can use REST.
REST.
Right. REST doesn't even use a neural network to draft. It retrieves actual code snippets from a database and uses those exact snippets as draft.
Oh, clever.
Yeah. There's also stage decoding, where you use a cascade of a tiny model, a medium model, and a large model. There's even self-speculative decoding, where the model uses its own early layers to draft and its full depth of layers to verify.
We have all these amazing techniques to speed things up. But if you are an infrastructure engineer deploying this at massive scale, we need to talk about latency versus throughput, because this is a crucial distinction. Speculative decoding makes a single user's text generate faster. But does it allow my servers to handle more users at the same time?
It absolutely does not, and that is a critical point.
Let's underline that.
Speculative decoding is strictly a latency optimization. It reduces the time it takes to generate a full response for a single user. It does not reduce the total FLOPs, the total mathematical computation happening on the GPU.
Because you're still doing the verify pass.
Right. In fact, when you factor in running the draft model and computing all those rejected tokens that get thrown away, you are technically doing slightly more total compute. Therefore, speculative decoding won't let you serve more concurrent users on the same hardware.
Let's use a carpooling analogy here to make it stick for anyone planning a system architecture. Think of GPU utilization as traffic on a highway. Speculative decoding is essentially bundling multiple tokens into one car. You're carpooling.
Good analogy.
If it's 2 a.m. and the highway is completely empty, carpooling gets everyone to their destination much faster because you aren't taking separate trips. That's a latency-sensitive scenario, like a single user chatting with an AI in their IDE.
But if it's rush hour and the highway is jammed bumper to bumper with thousands of cars, that is a maximum throughput scenario. Your GPUs are fully saturated, serving thousands of concurrent users.
Right.
In that scenario, carpooling doesn't suddenly create more lanes on the highway. You haven't freed up compute capacity. In fact, the slight overhead of those rejected draft tokens, the cars that take a wrong turn and have to be discarded, might actually hurt your overall system performance.
It actually slows things down if the system is fully loaded.
Exactly. If you are already compute-bound and maxing out your chips, speculative decoding isn't the answer. But if you are bound and latency is your primary metric, it is entirely transformative.
So what does this all mean when we zoom out?
Yeah.
Speculative decoding doesn't exist in a vacuum. It fits into what you might call the efficiency stack of modern LLM deployment.
Hmm.
You've got flash attention, which makes the massive attention computations fast and memory efficient. You've got the KV cache, which eliminates redundant recomputation across all those generation steps. And now you add speculative decoding, which drastically reduces the number of sequential trips you actually have to make to memory. Together, this stack is what makes talking to a 100 billion parameter model feel instantaneous instead of feeling like you're waiting for a batch job from the 1970s.
It's an incredible convergence of algorithmic cleverness and hardware awareness. But if we connect this to the bigger picture, it raises a really profound question about where AI goes next. Up to this point, we've only been talking about predicting the next 5 words of text, guessing sunlight instead of light.
Right. It's essentially very fast typing.
Exactly. But we've established a universal rule here. Verification is always mathematically cheaper than generation. And we know we can draft using external databases like REST or hidden conceptual states like e.g. So what happens when we apply this exact same paradigm to AI reasoning rather than just text generation?
Wait, what do you mean?
Imagine a future where the draft model isn't just spitting out 5 words of a sentence. What if a blazing fast, tiny model rapidly drafts an entire complex alternative branch of logical reasoning, or a dozen different pathways through a mathematical proof?
That is a wild concept to think about. So instead of drafting text, it's drafting entire thought processes.
Precisely. Could a tiny model draft a dozen distinct logic trees in milliseconds, and then the massive, highly capable target model simply runs one parallel forward pass to verify which reasoning path is mathematically sound?
Wow.
If verification remains cheaper than generation across complex problem spaces, speculative decoding might not just be a tool for fast typing, it could become a literal fast-forward button for deep AI thought. It represents a fundamental paradigm shift from sequentially generating tokens to rapidly searching through massive spaces of reasoning.
That completely changes what a language model even is. Imagine building a system where the draft is an entire architectural design for a code base, and the massive model just verifies the logic of that architecture in a fraction of a second. It's a whole new way to leverage parallel hardware.
It's the next frontier.
Something for you to mull over the next time you're waiting for a build to finish or a deployment to run. Thanks for joining us on this deep dive into speculative decoding. Keep building, keep questioning, and we will catch you on the next one.